Okay, so today it's about confidence interval and hypothesis testing. And let me start with the recap what happened last time. So last time we introduced not only continuous random variables, but all random variables, but continuous are probably the most interesting ones, because they sort of approximate discrete values at infinity, and infinity is a very interesting notion in mathematics. So a random variable can be defined by its CDF. By the way, can we remember what a CDF stands for? And as usual, you're welcome to write your answers in the chat. So let us remember what a CDF stands for. So what the abbreviation CDF denotes? Yeah, F for function. How about CD? Because there's also, if you look further, there's CDF, there's PDF, and there's PMF. And those are quite oftenly used in statistics and data science and machine learning. So it's useful to be able to understand those abbreviations easily. Yeah, C is not for continuous, but for something that is in fact seen from the first line. So the essence of this CDF is that it accumulates probabilities for a random variable. And as the value of, as we move further and cover more values of the random variable, the probability sort of accumulates. That's why CDF stands for cumulative distribution. And F, as mentioned, is indeed for function. Okay, so done with that one. And the random variable is called continuous if its CDF is a continuous function as opposed to, say, stepwise function, which happens for a discrete variable. And another way to define a random variable is either by its PMF for a discrete variable or PDF. So, well, the same question, what P and F stands for? Yes, and yeah, F is indeed a function. What would P and M mean? Yeah, very good. That's indeed probability mass function. Thank you very much. Well, and the last obvious question, what is PDF? Yeah, indeed, it's probability density function. Thank you very much. And yes, both functions of this kind, they include P for probability. And then the difference to notice is CDF and PDF, they both have D in the middle, but it's different Ds. So in CDF it's density, in PDF it's density, and in CDF formally it's distribution. So the notion is quite similar. And PDF and CDF are closely connected, and they can be derived from each other. Namely, one is the derivative of the other. PDF is the derivative of CDF, and CDF is the integral of PDF. Okay, so that was covered last time, and last time we also looked at different distributions, but we missed one interesting and very common distribution, which is also called normal because it's so popular, or Gaussian distribution. So let's do it today, and let's see why is it so normal and so important. So the normally distributed function is a two-parametric function, which means that it depends on two parameters, mu and sigma, and it's defined by its density, which has this form. So it's again our favorite exponent, and last time we covered the question why exponential function is so interesting and good, and the general reply is it's because of derivatives, because it's easy to differentiate the exponential function. This factor is just to ensure that the integral is equal to 1 on the whole line. So to make it a proper density function, we need to ensure that the probability of a whole, it's one of the axioms, is equal to 1, and that we can't get anything smaller, anything larger than 1 or smaller over the whole line. And those are the shapes of the normal distribution, well-known symmetric bell curve, so-called. So we all know again that the spike of this bell, or the highest point, is at the mu. So mu is also known as expectation or mean. And sigma is in fact standard deviation, the second parameter, and it represents the wideness of this bell curve. And you can see also why this density function is slightly more interesting than cumulative distribution function, because cumulative distribution function is, well, approximately always the same, from 0 to 1 and something in the middle, so not much difference in CDF. But PDF can indeed be quite more telling. And, well, actually, we've seen already this shape, didn't we? We've seen it when we dealt with binomial distribution with many repetitions. So here is the picture that you've seen already. Binomial distribution with different probabilities and the different number of repetitions, and, well, the shapes are very similar. Is it just a coincidence? And I suggested to see this experiment. I think you've all seen that, but let's try again. Do you still see the slides?
Yes.
Okay, I'll stop share and share a different screen then. I think you see another screen now, right?
Yes. Video.
Yeah. So this thing is so-called Galton board, or bean board. So what happens in here, we have lots of beans that come through a small slot in the, well, up there, and fall down, but the pegs, they add some differences or some randomity in probabilities for each of those beans. And nevertheless, all the beans fall forming the similar bell curve, which is essentially the normally distributed curve. So that's Galton box is a famous representation of a normal distribution, or rather, we can think of each bean as a Bernoulli experiment. So what we see here is multiple repetitions of binomial distributions, which indeed form this famous bell curve of a Gaussian distribution. Okay, so I will reshare. Can you see my slides back again?
Yes, fine.
Oh, great. Okay. Right. And it's not just a coincidence. And this all happens because of so-called central limit theorem. It turns out that if we repeat the same experiment many, many times, or in other words, if we are dealing with independent, identically distributed variables from the same distribution, so here I took the same variance is sigma squared and the same mean 0, which doesn't matter much, just for convenience. It turns out that this is true, that this sum normalized by square root of n will be distributed normally. And informally, it can be said or represented by the phrase that in the limit, any average is normal. And that's quite striking because it demonstrates that if you are dealing with repeated experiments and quite a large number of them, or if you are simply dealing with many instances, like many people, many beings, similar to that, then we can just model everything from a normal distribution. So that's an immensely powerful tool. And that's why very often we just assume that a random variable that we have no control over, that this variable is just a normal variable, because it seems to be quite a normal assumption. So let's see how it works further and what we can derive from this central limit theorem. So for a dice, for example, let's see how it works. So if we have just one throw of a die, then quite obviously it's not a normal distribution. By the way, what is the name of this distribution for n equal to 1? That's quite a characteristic distribution, and we've covered it, one of the first ones. So what is the name of this distribution for n equal to 1? So all probabilities are of the same value, and we have obviously 6 different probabilities for normal dice. So what is the name of such a distribution? Yeah, absolutely, well done. So that's indeed a uniform distribution, the distribution that we've started with. And for n equal to 2, the distribution is quite obviously not normal anymore, not uniform anymore. It's not the same probability at any value. And n equal to 3, it's even less uniform, and so on and so on. And even if n equal to 5 throws of a die already demonstrate quite a easily recognizable bell-shaped curve. Okay, and this bell-shaped curve allows some easy calculations of probabilities. So if you remember, the probability is the area under this function, under the shape. And it turns out that especially for normal distribution, the so-called sigma 2, sigma 3, sigma, or 68, 95, 99.7 rule is true. And it says that, well, obviously, the bulk of the distribution is around the mean. And if you deviate from the mean by sigma, one standard deviation, then we cover about 68% of observations of probability. And if we step by 2 sigma, then it's already 95%. And 3 sigma, we will cover almost everything, 99.7%, and so on and so on and so on. Well, obviously, we'll never cover the whole 100%, or we will cover it if affinity only, but 99.7 is usually high enough to say that it's almost the whole. So that's a very convenient thing in computations. Even more, to make it even further and more convenient, it's useful to consider, instead of any normal distribution, so-called standardized distribution. And to standardize, we just shift it by the mean and divide it by sigma to make it a normal with parameters 0 and 1. Mean 0 and standard deviation equal to 1. And then the density is written in much simpler terms, and then all the probabilities for x can be computed for the probabilities or for the standardized distribution for which tables exist. Well, it's not so important nowadays because we have calculators, computers, or can just Google this value, but it used to be a very important thing when just tables were available. So everything, any probability, should have been computed from those tables, which were, for obvious reasons, existed only for standard distribution, and every other distribution can be just derived from the standard tables. So another very convenient property of that. So, for example, we have a simple problem. So let's quickly just test our understanding. Suppose we have some kind of marks, like exam marks, with normal distribution, and we know that the mean one parameter is equal to 60, and another parameter, standard deviation, is equal to 10. And the question is, what proportion of the class has failed the exam, which means what is the probability of having a smaller than 40 result? And you're welcome to think about it. Well, it will, is it moving? Yeah, so it will be the same question if we just standardize the distribution. And then in the standard terms, we can easily see that it will be the same as finding the probability of falling below -2, which is 2.5%, because it's approximately as one side of the 2 sigma rule. So 5% probability should be divided by 2 to get one-sided probability, and the probability is 2.5. Any questions so far? So that was just a quick excursus into normal distribution, because then we are going to apply this normal distribution for more interesting things and find some elements of statistical inference. Okay, so what is statistical inference? What kind of it can we get? So the probability theory allows us usually to find exact parameters. But in practice, we have some kind of samples, and we would like to derive from those samples some outcomes from the whole population, or unknown true values, unknown true parameters. So drawing conclusions from some kind of samples for the whole population is also known as statistical inference. And there are several types. One first step is to differentiate between a point estimate and interval estimate. So a point estimate is just one number for a parameter, for example, exact number as a sample mean. And interval estimate is a slightly more relaxed thing, because then we allow our mean to deviate from this point estimate ever so slightly, and then we can define with what confidence we can say that our interval sort of catches this parameter value. That's a very imprecise formulation. Let's do it in more precise terms. Well, firstly, it's very important to check the assumptions. And the assumptions in this particular case is that we have a sample from a larger population, which we do not, the large population is not measurable in our particular situation, which is quite an important assumption. Otherwise, we would not be bothered by finding intervals at all. And we will see why in a moment. Another assumption is normality in this particular case, but similar approach is applicable for other distributions as well. And suppose that we are interested again in our particular case in finding the mean of the population, and suppose again that we know the standard deviation. And then let's see what can be derived from here. Suppose we have some kind of a sample, and this simple example again of some marks. So in front of us is a sample of 9 things, and what to do next? So we do the thing that is very similar to our beam machine. We think of any sample or any result as a result of different identically distributed variables. So we have 9 results, which means that we consider 9 random variables with the same normal distribution, with this unknown mean and given standard deviation. And suppose our standard deviation is equal to 15. And let me notice that this step is non-trivial and a bit abstract, because quite often we think that those samples are coming from the same repeated experiment and consider them as being representations from different independent variables was at the time quite a philosophic discovery in itself. Okay, so we have a sample, which means that from a sample, we can compute a sample mean, which will be just a point estimate, and in this particular case, it's equal to 60. Now, the mean is the sum of random variables, which means that we can consider it as a random variable itself. So, if you're interested in measuring this new random variable, let's try to see what kind of distribution this random variable has. Well, it turns out that this average random variable from central limit theorem will have the normal distribution with the same average but slightly different standard deviation. That is the standard deviation of each of them divided by the number of repetitions or the number of identically distributed variables. Okay, so why is it helpful? Well, because, well, by the way, that is also quite a strong property because not for any distribution we can say that if we add distributions with one to another, we'll get the same distribution. Why not? Because as we've just discovered, if we take many identically distributed variables, then in the limit, we'll get another distribution, which is a normal distribution. So if we've started with uniform distributions, then adding them together, strangely enough, will give us a different distribution, that is normal distribution. But normal distribution is again unique in this sense, because if we add the normal distribution with itself, we will get a normal distribution again, which means that it's stable distribution under addition. There are some other distributions, not many of known ones, which also have this property, and I think the most interesting one will be covered next time. But for now, let's move further. So in our particular example, the standard deviation of the new average or mean value, mean random value, will be equal to 5. Now, so this approach, in fact, is applicable in two cases. And now I'm deviating slightly from this particular example. So firstly, we can do exactly the same thing if we start with normal distributions, because as mentioned, adding up normal distributions will give us a normal distribution. When distributions are not normal, but still identically distributed with finite mean and known variance, and if the number of those distributions is large, then we can also think that this mean will be a normal distribution from the central limit theorem. But to go to the limit, we need a large number of repetitions. So as a rule of thumb, as n should be larger than 30, but it's a rule of thumb, which is very, very rough. And what happens in real life, if this rule of thumb is not really applicable, again, we'll cover on the next lecture, next session. But what happens if we don't have known standard deviations, for example, or if the number of experiments is quite small? It turns out that we can do a very similar thing, but then the mean can be approximated not by a normal distribution, but by a so-called t statistic. And it turns out that this t statistics will follow so-called student t distribution with n-1 degrees of freedom. And here we bump into another distribution that we didn't come across before. So what is a student distribution? So student distribution is some kind of generalization of a normal distribution. And you see the shape is very similar to the normal distribution. It's also symmetric. It's also bell curved. And the main difference is in the tails. So it turns out that in student distribution, generally the tails are heavier, that is, contain higher probability. And it becomes the normal distribution only if a parameter goes to infinity. Well, if the number of repetitions is large, similar to our central limit theorem. And you can see on this picture, so the parameter equal to infinity corresponds to that black curve with indeed very, very small tails. And that again quite conforms well to the sigma 2, sigma 3, sigma rule, which states that we don't have much beyond the 3 sigma. It goes to 0 quite quickly, the weight, the probability. Well, and student distribution also is distributed, roughly speaking, around 0, which is represented by this fact that expectation is equal to 0 for the parameter bigger than 1. And funny fact, well, why is it called students? Is it because of pupils or students? Well, nearly. Student, in fact, was a pseudonym for William Gossett, quite a well-known statistician who did quite a lot in mathematics and statistics. He was also a chemist and head brewer of Guinness for quite a while. And I wonder if this scientific approach defined the fact that Guinness, you know, this beer mark, the Guinness beer is still so famous around the world, and the quality is quite good, I think. Because it was based at some point on true science. Okay, so what's next? If we know how our average or our mean is distributed, then we can apply the relevant rule of distribution. So for a normal distribution, it will be this sigma 2, sigma 3, sigma rule. And then it says that almost everything will be inside 2 sigma from the mean. Well, approximately inside 2 sigma, but in fact, from the tables, a slightly more precise value will be 1.96 sigma. If we're dealing with students distribution, then we don't use this rule, but similar approximations for the probabilities exist for students tables as well. So assume we are dealing with normal distributions from now on, because for the student distributions, all the steps will be very similar, just from a different table. Okay, so we know that the probability to get away from the mean or not further than by 10 is equal to 0.95, because 2 sigma in this particular case, sigma is equal to 5, will be equal to 10. Which means that we can be 95% confident that our average should be not further than 10 away from the approximated point estimate. So, well, the value of this deviation from the point estimate is known as the margin of error. So we now have everything that constitutes, well, that makes up the mechanism of confidence interval definitions. So in a general case, we are able to find so-called critical value. And critical value is just such a number that our variable is closer to the mean than this critical value, or the probability to get not further from the mean is equal to some number alpha. This alpha is known as a confidence level. And then we can say that for a normal variable, the mean should belong to the confidence interval, which is defined as we've defined before. We take the point estimate and then add the margins of error, as we did before. And then we can say that if we repeat this procedure many, many times, that we can be confident that the confidence interval will cover the true value of the mean with the given probability that is confidence level. Well, that's all sort of obvious, but one of the main catches, which is done again and again and again by people, is saying that the confidence interval will catch the parameter. And that's something statisticians try to battle against, because by the very essence of frequency statistics, that's not the right thing to say. Why? Well, let's look at the following example. So this example represents samples from exactly the same normal distribution and with a 50% confidence intervals computed for the mean. And as we know, it's a synthetic example, so we know the true mean for this normal distribution, which is represented by this dashed line in the middle. So we can see which intervals will contain this true value and which do not. So the blue ones are the ones that indeed do contain the true value, and the red ones are the ones that do not contain it. Which means that, well, whilst the confidence interval has been computed, it's done. And we cannot say that that it will catch or will not catch the parameter. They are all known. It's all done now. and the true mean either belongs to the computed interval, as for example on line 4, or it doesn't, as for example in line 1. So saying that it will somehow magically catch in the future, that's not the right thing. Well, that this can not right. So saying that this confidence interval catches the true parameter is not exactly right. What we can say is that if we repeat this experiment and this process many, many times in the future, that is both sampling and applying the computations, then we can be confident, with a given confidence, that the interval will indeed cover the true value. But for a given and already calculated confidence interval, it's just meaningless to say. A bit of philosophical notion here. And for higher confidence interval, what will happen to the confidence with a higher confidence level? What will happen to the confidence interval? Should it be narrow or wider? If you would like a higher confidence, what should happen to the confidence interval? Will the confidence interval become wider, or will it become narrower? That's, by the way, one of the typical interview questions for anything like data science interviews or even quant interviews. So what will happen for a higher confidence level? What can we say about the confidence interval? And the answer is that for higher confidence level, we require the interval to cover a larger probability, which means that the interval should become larger to accommodate for a larger margin of error. So that's like a balance of that. Okay, so that was one type of statistical inference. We were defining the interval around the suggested parameter. There is another type of inference, which is known as hypothesis testing, which is that we are not finding some kind of interval, but we would like to test some kind of a claim. For example, if we flip a coin and get one head, but then lots of tails and no heads in sight. Well, may I ask how many personally you would like to experience before you can claim or suspect that the coin is biased? I don't think that there's right or wrong here, so it's just interesting. Can you give what will be, how many tails will be the sign of for you personally that the coin is biased? Oh, I can see 10 there. Any other ideas? Yeah, so maybe 2 is a bit too low, and in fact not seeing 2 and having perfect sequence of head tail will be slightly suspicious. So maybe 2 tails will be fine. How about 3? How about 4? And I should admit that I don't have even an answer for myself, because that's a non-trivial question, isn't it? But it's nevertheless quite an interesting one. At which point we can draw a line and say that I've got enough, and you're definitely not demonstrating a fair coin here. Well, that's the essence of the hypothesis testing mechanism or apparatus or tool. So we make some kind of guess, but this guess should be testable. And then we can call this guess a hypothesis. And usually we state a null hypothesis, and usually it's something that we knew before as a fact, and we would like to check if it's true or not. For example, for the coin, maybe that's the initial idea or claim that the coin should be biased. And we would like to check this null hypothesis. And the name comes from the fact or from the statement that null hypothesis should be a nullifiable hypothesis, which means that we should indeed be able to check it. And then, after we check it, we either can reject or nullify it in favor of alternative hypothesis, or we can fail to reject it. And there's quite important thing to remember, that we can never say that we accept the null hypothesis, because it's a bit like trying to prove a theorem by repeating an experiment or by testing many examples. With every new example, we can find a counterexample, and then indeed a counterexample, even one counterexample, can nullify the statement. But how many examples should we check, usually, to prove the hypothesis? If we have infinitely many cases, as we do in continuous distribution as opposed to discrete distribution, then we can never check all infinitely cases, which means that we can never exhaust everything and say that we've checked everything and we can accept the hypothesis. So that's quite an important thing to remember, and it's quite a common mistake. So we never can accept the hypothesis, but we can reject it. And often we are more interested, in fact, in an alternative hypothesis and sort of formulated before formulating the main hypothesis. So, for example, in the experiment of flipping a coin, as mentioned, nullifiable hypothesis, null hypothesis, will be probably the hypothesis that it's a fair coin. And you are welcome to think about what will be the nullifiable hypothesis, for example, in Galileo's motion and heliocentrism. But I suggest us to, well, have some rest and think if the following statements can be thought about as a valid null hypothesis. So, for example, number 3, all unicorns are pink. Is it a valid null hypothesis? And if yes, why? And if no, also why? Any ideas about the validity of hypothesis that all unicorns are pink? So can we state, can we choose as a null hypothesis the following statement: all unicorns are pink? Yes, it seems hard to test indeed, or I'd say it's even impossible to nullify. So remember that the null hypothesis should be at least theoretically nullifiable. which means that in this particular formulation, without, say, specifying what a unicorn is or what kind of unicorns we consider, maybe if it's toys, then it's indeed not only hard to test, but impossible to test. Well, how about the second one? Earth is flat. So the same question is for a valid nullifiable hypothesis. And I personally think that this number 4, that Earth is flat, is quite a sort of perfect example in this case, because that's an old statement that humanity held for many, many, many years or centuries, that the Earth is flat, right? And there were many attempts to accept this hypothesis, and attempts usually consisted of, going as far as you can, not finding the edge of the Earth and saying, oh, look, I haven't found the edge of the Earth, which means, well, I haven't found the edge of the Earth, which means that we cannot nullify this hypothesis, yeah? Or at some point, I didn't go round and didn't come to the same point, which means that the Earth is not round. And it was probably not a valid hypothesis, again, for many centuries when humans were not able to test it. But at some point, just one journey across the globe was enough to reject this hypothesis, which means that it turns out to be a good and valid nullifiable hypothesis. Well, and the last example about the goldfish, probably again, is just a bit hard to test, isn't it? Because then, well, we can have and keep goldfish and guinea pigs, but then the problem is with the word better, because measure that will be a bit hard, which means that nullify the hypothesis will also be a bit hard. Okay, and that's stating the hypothesis is a very important part, because that's the very first step of what we need to do. Now, after nullifiable hypothesis, there is an alternative hypothesis. And it turns out that there are two types of alternative hypotheses. So I'll just skip that one and we'll demonstrate it on the following slide, following example. So null hypothesis is stated, for example, we take a null hypothesis, the statement that the mean of exam marks is equal to, say, 60. But then as alternative hypothesis, we can take so-called clean alternative, just saying that the mean is not equal to 60. But in practical terms, quite often it's convenient to take just one-sided alternative and check the fact that state as an alternative the statement that the mean is higher than something, or say lower than something, in which case the alternative hypothesis is called one-sided. Why is it possible to do? Well, remember the shape of the normal distribution, because it's so symmetric. To get from the sort of full alternative hypothesis to one-sided hypothesis is very easy. We just divide the both sides or both tails by 2 into one tail. But that's quite a unique property for normal distribution, which will hold for some other distributions like student's distribution, but not for all hypothesis testing cases. Right, okay. So we are ready to state all stages or steps of hypothesis testing. And we've so far discussed it on the example of normal distribution, but it is applicable to any kind of hypothesis testing, which again, we will see on the next session. Okay, so the first, most important step is to state null hypothesis and define it in a correct way so that it can be nullifiable. The next step is to state statistical assumptions or assumptions about the sample, the problem, the example, whatever. And because we need that, because the third step is to choose the test. So choose the appropriate distribution test or statistics that we can measure and decide what to do next, nullify the hypothesis or not. In practice, usually the test is chosen at the second step just from the list, and then we check the assumptions forward, sort of swapping steps 2 and 3. So we've covered 3 of the steps, but for the next steps, we need new definitions. So assume that the null hypothesis is true, and then we found some kind of statistics, that is numerical measurement tool to measure some kind of result of the experiment. And then another important notion is the p-value. And the p-value is the probability to obtain a result this or more extreme than the one that we observed. Or more precisely, p-value is the probability of getting this or more extreme result if we assume or conditioned on the null hypothesis being correct. So how can we, what can we do next? Suppose in the same problem with student marks, suppose that our experiment demonstrated that the average mark turns out to be equal to 69 instead of 60. So this observation sort of casts doubt on the initial hypothesis of average of 60. And to quantify this doubt, we need to consider the p-value, the probability of having 69 or more extreme, that is 69 or more. Or if we are considering both sides, two-sided p-value, then we consider the probability to deviate from the mean more than by 9. And again, in the picture, it can be seen like that. So one-sided p-value is in the first picture, two-sided p-value is on the second picture. If we define that, then we can compute further. And to make things just a bit more convenient, we do similar kind of normalization and consider so-called Z statistic. So for normal distributions, the Z statistics is the normalization by taking away the mean and division by the sigma divided by square root of n, which is done for the same reasons as the reasons that were used for, well, central limit theorem, so the same mechanism as for the confidence intervals. Because then we can say that this normalized standardized set statistics will be normally distributed with mean 0 and deviation 1, and then we can easily use the usual calculations and tables. Okay, so suppose we computed the Z statistic for our particular case, and we've got that our Z value is Z is equal to 3. And then we compute the p-value of probability being further from the mean than 3. And this probability is known because we are dealing with a known distribution, which with a normal distribution. which means by the sigma 2, sigma 3, sigma rule, this probability is 0.3. So we all done, we measured everything. What can we say now? Can we reject the null hypothesis or not? So we've computed everything, but how about the final decision? What can we do? And this picture demonstrates what's going on, the mechanism of taking this decision. So if p-value or probability is high, that the result is sort of probable, that we do not reject the hypothesis. But if our probability is small, or the obtained sample is quite improbable, like in the case of having 10 tails in a row, then throwing a coin, then probably we can reject the initial hypothesis. So that's how the mechanism looks like. So in our example, if do all the calculations quickly, then we can say that 0.3 is quite small indeed, which means that probability is indeed small and maybe we can reject it. But that very much depends on the level. So if we don't need a lot of precision, if, for example, our confidence significance level is 1% or even 0.5%, then we can say that this probability is very small and we can reject the hypothesis. But sometimes we need more precision, and in that case, we would like to have a lower significance level. And in this case, we cannot reject the hypothesis. So what happens if we change something? For example, what happens if we had another kind of sample, 66 instead of 69? Well, we will repeat the same kind of steps. In this case, we have a normalized value equal to 2, which means that the p-value will be equal to 5%, right? Which means that now it will be significant at 5%, but not significant at 1%, as we had before. Why is it useful to understand? Firstly, because we can compare the one-sided p-values and two-sided p-values, and we can see that one of the sort of ways to get the significance on the cheap is just to consider one-sided p-value instead of two-sided, because obviously one is 2 times larger than another. And also, probably from this table, you can see the sensitivity of everything that we decide on the chosen p-value. So small deviations can lead to different decisions. And there's a famous cartoon just about that. So what happens if we take different p-values? If p-value is small, we say it's highly significant. Well, if it's larger, we might say that it's significant. If it's exactly 5%, wow, that's a bit of indecision here. But suppose we have just 5% and we are really, really keen to publish, then there are some other inventions. We can say that the result is on the edge of significance, that it's highly suggestive and still significant at some level, which is true. Well, and so on and so on. Which means that ideally, or always, significance level should be set before the study. And that's why traditional values of 5% or 1% are usually used and utilized. But as we'll see next time, ideally, this should not be set in stone. Because if you have lots of parameters and lots of values, as happens, for example, in contemporary genetics or contemporary data science, then that should be represented in a lower significance level as well. because those historical figures of 5% or 1% were created almost a century ago when large data and large calculations were not heard of. But that I'll try to cover next time. Right, so what essentially happens for hypothesis testing is, we try to achieve some kind of threshold or some kind of balance between two situations. Between false positive, rejecting something that is actually true, and false negative, that is failing to reject something that should be rejected. And hypothesis testing can be seen as a very, very, very fragile attempt to balance those situations. And now we've covered all 6 steps of hypothesis testing. The first one is very important, choosing a hypothesis. The second or third one is choosing a test. Another important one is checking all the assumptions, then setting a significance level, then calculating, getting the number, and the last step is to compare this number with the significance level and finally make a decision. And please remember that we can never accept the null hypothesis, even if there's not sufficient evidence to reject it yet. Well, and another important quality is the sample size, but again, I'll briefly cover it next time. Okay, so today we've covered 2 important things from the normal life that are virtually used everywhere. That is central limit theorem. In the limit, everything is normal. That's why we can find confidence intervals. That's why we can perform hypothesis testing on everything around us. Well, and in the infinity, everything is normal. At all approximations, all models are wrong, but some models are useful. So the question similar to hypothesis is probably not if the model is true, it never is, but if the model is good enough for this particular application. And that is not a trivial question. In other words, well, in theory, we've sort of proved that in many cases, normal approximation is good for everything. But is it true for this particular application? That's the question for the next session, but that's all for today. And that's a homework problem to test yourself on, but that's all from me. Thank you very much and have a nice weekend.
Yeah, thank you, Olga. Thank you, Marjan and Henry, for coming today. Olga, did you say what will be the final topic next week?